Okay, I'm going to charge into this so you can get a little chance to work today.
Is there a new assignment up?
No, the new assignment's in the book. You guys see that?
I never got it.
Okay, so let me, before we do anything, let me show that to you.
Just throw it on. I never got it.
We need to get your book. So grab one, and then I'll just.
Can I get a book? Never mind, I got a book. I think I got it.
You got a book? Okay. Okay, so this is what the assignment looks like. Okay, Unit 1, 1.3, one-sided limits. So notice that these are, there's the reading, and there are the assignments. There are the assignments, right? So they're paper and pencil. So there's one of them. If you click on it, it just says the same thing it does right there. So you're doing Larson 6, so that's your textbook. Page 76, 5 through 25 odd is the first assignment on one-sided limits, then infinite limits. It's Larson 6th, page 84 and that stuff. Okay. I will put up solutions to those also. Okay. I think I assigned all odds. I tried to. I think I did. So you know the odds, the answers are in the back for the odds. So you can check them as you go. Okay? I updated all my calendars for my other classes yesterday. I'll do yours today. So this is, how about, what's today? Wednesday?
Yes.
So the first one, let's say Friday, second one Monday. That's fine. Those, once again, those are just going to be dates for you to keep them, to make sure you're staying on track. But I probably won't actually put them in the book until a few days after that. So, okay. Question? I'll collect them. Yeah. Or I may not actually collect them. That's going to be a pain because I want you to have your possession of them too. What I may end up doing is I'll publish the solutions. I'll have you guys give yourself grades based on if you did everything and used the solutions, and just give yourself 100 on it. Okay. But you got to do them. These are really important questions. You got to make sure you get this practice. That's really the key.
It's practice, so it's rather inconsequential to our grades.
Right. It doesn't even hardly matter, but it will in the test. Okay. So let's have a look at this. One-sided limits. Okay. What should we try first here with this one? Try to directly substitute or directly evaluate. If we do that, does everybody see that we're going to get a number divided by 0? Okay, if we try to evaluate directly, we get -1 over 0, which is no limit, right? Okay, but we want to do better than that. So we got a one-sided limit, so what can we do? We kind of started talking about this stuff yesterday. Oh my goodness. So we're approaching 2 from the left. So we did some stuff like this yesterday, and remember we said things like if we evaluate this limit right here, as we approach 1 from the right, that's going to be 1 minus a number slightly bigger than 1, which gave us 3 over 0 minus, right? If I get a number divided by 0, I already know automatically I'm getting an infinite limit, but we just need to know the sign, right? Positive divided by negative gives me negative. This is a little tougher. If I try to evaluate this directly, it's going to be kind of hard to do. I'm going to get something like 2 minus squared would be like 4 minus, right? Minus 2 times 2 minus would be something like another 4 minus, I guess, right? It starts to get complicated. That's a bad way to do it. We'd like to factor it if we could. If we can look at a product of factors, it's easy to determine the sign. We just follow the sign rules then, right? So we don't want to try to do anything tricky with this. We first want to write everything in factored form. Top's already factored. What's the bottom factor into?
X and X minus 2.
So x times x minus 2 as x approaches 2 from the left. And we already know that because we got this 0 on the bottom, we're getting infinity, right? The question is just what flavor of infinity. We need to know the signs of each of these factors. So what's that going to give me? The sign of the top, as x approaches 2 from the left, the top becomes negative, right? It's negative 1. So we've got a negative sign on the top. This factor is going to be 2, so it's positive. We don't even care what the value is, it's just positive. What about this one?
Positive.
It's going to be a negative, isn't it? Right? Everybody see that? We're going to get, because we're going to get 2 minus, so that's like 1.999, right? Minus 2 is going to give us something negative, right?
Yeah.
You see that? And so the overall sign then, if I've got a negative divided by a positive times a negative, I've got 3 total factors here. I've got an even number of negatives, so what's the overall sign?
Positive.
Positive. Okay, so what if we hadn't done this first, tried to evaluate it directly? We could have written this last step slightly differently. We could have just written it as negative 1 over positive 2 times 0 minus, right? Same thing. Now we can see that because we end up with 0 on the bottom, we're getting something that's infinite, and I can still just look at the signs and see that I'm going to have an overall positive sign, right?
These are infinite constants.
So these are infinite limits. Infinite limits because we're getting infinite answers, right? So these always correspond to asymptotes graphically. Question?
There is factor on the bottom.
Mhm. Because as x approaches 2 from the left, that's going to be a number slightly smaller than 2,
Oh,
right? Okay? Make sense?
Yeah.
Question?
When approaching one-sided functions like that, is the
One-sided limits?
One-sided limits, my bad. Is the reciprocal of that, the 2 plus, always going to be the opposite of the?
No. Not always, because what if that was, for example, the quantity x minus 2 squared?
It would be positive.
Yeah.
So it works the same as any other function what we have talked about.
Yeah, but rather than, I think looking for generalities and patterns there is going to be kind of fruitless. I think you just want to evaluate the factors each time. Yeah. Okay, what about this one? You can do it pretty quickly.
Doesn't exist.
Doesn't exist, right? How come this one doesn't exist, but this one we got an answer?
One-sided limits.
It's a one-sided limit compared to a two-sided limit, right? The one-sided limits actually don't exist, right? But we at least know how they don't exist. We can be specific. In which direction are they blowing up? In this case, we can't. Yep.
So one-sided limit will always have a negative also for x.
Yeah. Yep. Yeah, you know it's a one-sided limit. That's what tells us it's a one-sided limit. Right there. Okay.
But so if it doesn't have that, it needs to have that.
So if it doesn't have that,
No.
then it's implied that it's a two-sided limit. Right. Okay? Okay, last issue, greatest integer function. I want to introduce you to a new function. I can't remember if I might have just showed you this in Algebra 2, but it would have been brief and it wouldn't have meant that much. The greatest integer function, here's what it does. Here's the way we symbolically represent it on a calculator. A lot of times, it'll be int of x, I guess for integer. Another way you can do it on calculators, another function that they'll use, well, I'll tell you in a second. So what this does, when you input a value, it's going to return the greatest integer that is less than or equal to the input. Okay? So I'm gonna input a number, and I'm gonna take the greatest integer that's less than or equal to that input. So what's the greatest integer of 3.1? 3, right? What's the greatest integer of 19.9? No, 19, right? Because 20 is too big. It's gotta be the greatest integer that's less than or equal to the input, right? What's the greatest integer of 2? 2. About 0. Negative 0.5.
Zero.
Negative 1, right? Because 0 is greater than negative 0.5. Does that make sense? So there's a way you can kind of think about it. Here's how I like to think about this. If you, for the greatest integer function, here's one model for understanding this. If we draw a real line and we've got all our hash marks on the integers, right? Imagine those are knots on the infinite line, and we're gonna, a bead represents the location of an input value. So if I input something like 3.3, I'm just always gonna slide the bead to the left until it encounters a knot, right? So it would be 3. If I stick a bead right there at negative 2.2, I'm gonna slide it to negative 3. If I put it on 0, well, it's already on a knot, I can't slide, right? See what it's doing? So what does that look like as a graph then? That's gonna be, yeah, it's gonna be stair steps, isn't it? Right? Here's what that looks like as a graph. Let's see, am I somewhere? Yeah. Okay, there it is, right? You see that? Okay, but graphing calculators do a crappy job of endpoints. What am I going to do with the endpoints on this? So let's just start right here. I've got this flat step, but what do I do like at this endpoint right here? It's going to be a solid dot, isn't it? Right? Not a hole. Opposite of a hole. It's going to be a solid dot because if I input a 0, I get back a 0, right? If I input a 0.9, it slides all the way over and I get back a 0. But if I input a 1, I get a value of the function of 1. So I'm going to have open circles or holes on the left of each step and closed circles, or on the right, and closed circles on the left of each one, right? And the graphing calculators don't do a good job of displaying that. Now we could check it and see to demonstrate, like we could do something. Here, let me just do this. I want to preserve this for your notes. So let me take a picture of that. There we go, okay? I could evaluate the function. I've written this as a function g of x. So in Desmos, I could do something like I could do g of 1. Oops, g of 1. There we go. G of 1 gives me back 1, right? So I can see when I go over 1, I go up 1, right? And I could even do, if I want to be really tricky, I could do some points. Like I could do the ordered pair A, G of A. Let's add a slider for A. And we'll go from -5 to 5 by 1s. Actually, let's go by 0.5s. Better. Okay. So let's see what happens when we scoot along, get to the end and it pops up. So we can see that if we evaluate the function at an integer, it knows what to do, but you just can't tell from the way it's displayed, right? Look what it calls this. It calls it a floor function. Okay, that's another way of saying greatest integer function. Just an embarrassment of riches here, because we could call this a floor function. Floor means you're just gonna push it down to the next integer, right? You're always gonna drop it down to the next available integer. What if I wanna push it up to the next available integer? Like I wanna input an 8.7 and get back a 9 instead of an 8. What do you think I call that function? Ceiling function. Yeah. What did you say, Gabe?
Rick said he was gonna say roof.
Oh, roof. So look what happens if I turn on the ceiling function. There it is. It's the green one. Look what it did. It just scooted everything up vertically by 1, didn't it? Just lifted all the stairs up by 1. Okay? So next issue then, I want to look at one more thing with this. And this is I like this. This is pretty good stuff here. So I want to know. Oops. Let's take the function, the greatest integer function, or floor of x over x. Okay, what's that going to look like? Well, let's look at the places where it could be a little dicey is going to be when we make the transitions, right? The integers. So let's take an example of one. Let's look at something like 0. How about? What's going to happen at 0? As I approach 0 from the left and 0 from the right, what am I going to get here? Let's maybe do another one first. How about, before we do that, let's do the limit of f of x, and that's f of x, right here. As x approaches 1 from the left, what am I going to get? So if I evaluate this thing, I can evaluate this directly, can't I?
0.
If I approach 1 from the left, the greatest integer function is going to give me 0, isn't it? Right? So I'm going to get 0 divided by 1, which is what? 0. Okay. If I take the limit of f of x as x approaches 1 from the right, what do I get on the top? 1. On the bottom? 1. Okay. So we can see what's going on there. I'm going to get a jump in the function, aren't I? Right? You see that? But what about at 0? What's going on at 0? If I approach 0 from the left, what kind of answer do I get? What's the greatest integer function of 0? It'd be -1, wouldn't it?
Yeah.
The floor function. It's going to push that bead from -0.0001 all the way down to -1, right? So I get -1. What about the bottom? 0 minus, right? So what's that telling me? Yeah, I know I'm getting infinity because I got a 0 on the bottom, and I know it's going to be a positive infinity because negative divided by negative is positive. Great. Okay. What about this one? The greatest integer of 0 plus is 0 divided by okay, what's that answer? What is it?
0. How come? 0 over oblique.
Okay, yeah, it is. It's 0. Because the top is exactly 0, isn't it? The output is precisely 0. The bottom is not. The bottom is a small positive number. Doesn't matter how small it is, if it's a number and it's positive, how much bigger is it than zero itself? Infinite, right? So yeah, so there's a difference there. So zero divided by any positive number, regardless of how small, is zero. Got that? Okay, so let's look at the graph of this thing and see if it matches what we predicted. There it is. Okay. It did what we said, didn't it? We said that as we approach 1 from the left, we got 0. As we approached 1 from the right, we got 1, right? So we had a gap there, so the functions, there's no limit at 1. As we approach 0 from the left, we got positive infinity. Okay, we can see that. There's an asymptote that shoots upwards, right? As we approach 0 from the right, we got 0. So it's a weird looking function, but that's what it looks like. Okay, so the next step, we're not going to do this today, but the next step is going to be, we're going to use all these tools that we've developed with limits to talk about the concept of continuity in a function. Like if we take this one, do you think, just out of the blue, we haven't even talked about it yet, do you think this function is going to be continuous? What's your gut reaction to that?
Yes.
I'm hearing a yes, I'm hearing a no. Well, how come yes?
I just see the reason
Why what?
why it determines it.
Okay. What do you, Gabe, how come you're saying no? Okay. And I haven't even defined continuity, but that's actually what we're looking at. Continuous means, here's a way to think about this. So before we even jump into the continuity discussion, which is our next discussion, a function is continuous if I can draw it without picking my pen off the board. Then it's continuous. If I have to pick my pen off the board, then I broke it, right? It's not continuous. I had to do it in pieces. Okay? So this is clearly not a continuous function. It's continuous in places, but there's a lot of places where it's not continuous, right? And I bet you can already start to maybe see how that might be related to the concept of one-sided limits. Right? Okay, I'm done. You may work.